The final topic I want to look at in this chapter on Fourier transforms is on signal energy. If you recall, the signal energy is defined as the integral from minus infinity to infinity of x of t squared of dt. You might ask why we have the absolute value if we're also squaring. It's because this definition even extends to the case in which x of t might be a complex signal, although we haven't been working with complex signals in this particular course. You can show, and I'm not going to go through the proof, it's in the textbook, and this is Parseval's theorem, which we saw previously when we were discussing Laplace transforms, that we can also calculate the energy from the Fourier transform of x of t by integrating over the square of the magnitude of x of omega. In this case, the absolute value is necessary in the frequency domain because in general x of omega is a complex function, and the magnitude of that is an entirely real function. So this is Parseval's theorem for the Fourier transform. We can find the energy within any particular frequency interval, and this is where Parseval's theorem is of particular usefulness, by integrating over the corresponding band of frequencies. So we can find the energy out to a frequency capital B. This would include the energy in all frequencies from 0 to B. Since x of omega is an even function for a real x of t, we can also write that the total energy is 1 over pi, and then instead of going from minus infinity to infinity, go from 0 to infinity and then double it. That's why the 2's cancel out here. So x of omega squared d omega, or for the energy within the frequency range 0 to b, similarly I can just integrate out to b. I can also extend this definition to get the energy within any particular frequency band, say between omega 1 and omega 2, by just integrating over that positive frequency range. So let's look at an example problem. This is problem 7.6-6, where we're given x of t is equal to 2 times a over t squared plus a squared. We can compute the energy in the time domain, minus infinity to infinity, of x squared of t dt, or the integral from minus infinity to infinity of 4a squared over t squared plus a squared squared dt, and then looking this up in a table of integrals or using your favorite symbolic computation software, the total energy contained in this particular signal is 2 pi over a. Alternatively, we can find the energy using Parseval's theorem. The particular, you can find the Fourier transform of x of t by actually using duality. the Fourier transform of x of t is 2 pi e to the minus a omega, and then so the magnitude squared will be 4 pi squared e to the minus 2a absolute value of omega. And then we can calculate the energy also in the frequency domain. It's 1 over 2 pi integral from minus infinity to infinity of the magnitude of our magnitude spectrum squared. Okay. Again, because of the even nature here, even symmetry of x of omega, I can integrate from 0 to infinity and just double that result, 4 pi squared. And for omega between 0 and infinity, the absolute value of omega is equal to omega. It's another good reason to invoke symmetry here. Saves myself a little work. This, I don't need to resort to a table of integrals in this case to actually solve. To integrate this, it's just an exponential function with integral 1 over minus 2a. Evaluate that at the limits, and we also get 2 pi over a, which we should. This is just a verification of Parseval's theorem. But we can also find the energy in the frequency range from 0 out to an upper bound b. We'll be integrating from minus b to b, and we're again invoking symmetry. 0 to b of 4 pi squared e to the minus 2a omega d omega. Carrying out that integral, I actually get 2 pi over a 1 minus e to the minus 2a capital B. Okay. This result is actually less than the total energy. Of course, it should be. Notice that if I let b become infinite here, as b tends toward infinity, this term goes to 0, and this result reduces to the line above. I might be interested in answering the following question. In what bandwidth b is 95% of, or 99% of the energy contained? In that case, what I want to do is actually set EB equal to, I'll use the 0.99 example, 99% of the total energy, and then solve this, and then solve for B. So what I want to do here is take this expression, 1 minus e to the minus 2ab, and then set it equal to 0.992 pi a, which is the total energy. Of course, this term cancels out. I'm going to have actually taking the 0.99 to the left-hand side, and have 0.999 is equal to, and taking this to the right-hand side. I can take the natural log of that result and of both sides, and then solve for b, and I'll get b is equal to the natural log of 100 over 2a, or 2.303a. So the 99% bandwidth here depends on the value of a, which is a parameter in our signal. And it's, in this particular case, 2.303 divided by a.